All right, so let's get started. Again, I just want to remind you that homework 2 is due tomorrow, okay, by midnight. Um, and then for classroom disinfection for today is assigned to Connor and Isaac, okay. All right. So last time we talked about heat transfer, specific heat, and calorimeter. So basically you have two objects in place in contact. If there's a temperature difference, then there will be heat transfer from the hot object to the cold object, okay? And um, Joule has demonstrated that heat is equivalent to energy because he can convert mechanical energy into heat here. All right, and then if you have heat added to an object, then the temperature of it will increase. If you take out heat, it will decrease, temperature will decrease. The relationship between heat and temperature changes in this expression. In the case there's no phase transition, okay? If there's a phase transition, then it's a little bit different. However, if you have two objects in contact, then the energy should conserve. So Q cold plus Q hot should equal to 0, right? So that's calorimeter, how it works. In some cases, in extreme temperatures, the specific heat capacity is temperature dependent, all right? So then in that case, you want to use the derivative form for this guy or for the Q, all right? If you want to calculate Q, then you want to start from here. All right. For phase transition, we talk also about phase transition. So when phase transition happens, there's latent heat. All right. If you have, say, a liquid in a confined container here, then there will be vaporization happening and also condensation happening. Depends on the temperature. You will have a vapor pressure that is depending on the temperature. So that's and when these two processes in equilibrium, okay? So it's called equilibrium vapor pressure, and the equilibrium vapor pressure determines what the boiling point of a liquid, okay? So if you have more pressure, then boiling temperature will increase, okay? So that gives you a sense what's the boiling temperature with respect to the pressure. For a P versus T, it's also called phase diagram. So in the diagram, you probably can find what state is the substance under certain condition, okay? So that's a simple phase diagram for water. Latent heat, so when you have phase transition, then there's wait a second, I need to share screen here. Forgot about that, but all right. So latent heat, when you have a phase transition, then the heat added or removed from the substance will not change the temperature of it, okay? So in that case, then it's not simply just linear responses of heat added and then the temperature change, okay? We will take a look on that, but later, one of the examples. So latent heat is defined as latent heat is L, symbol L, but Q is equal to M times L, okay? So latent heat is the heat per kilogram that's needed for phase transition. Sometimes the phase transition happens directly from solid to vapor and from vapor to solid as well. So that's called heat of sublimation for the latent heat in this case, okay? And we were about to look at this problem last time. So this one says you have a 1.1 kilogram block of ice initially at temperature of -5 degrees Celsius. If 5.2 times 10 to the fifth joules of heat are added to the ice, what's the final temperature of the system? All right. It gives you specific heat. For water is 4186, and for ice is 2090 joules kilogram times degree Celsius. The latent heat of ice melt is 335 kilojoules per kilogram. All right. So you're going to determine what's the final temperature of the system of the ice. It might be melted already. So let me get you guys started with what could happen. Okay. All right, let's see. Just need to switch the camera. All right. So this is what you are going to do with this type of problem. Okay, you're going to have a vertical axis as temperature, degrees Celsius. You're going to have Q as the heat added as the horizontal. This is 0 degrees Celsius over here. Okay. So as you add heat into the water or into the ice here, ice is -5 degrees to start with. Okay. So then heat added, temperature will rise. So it's linear response. Okay. So you can see at certain point, it's going to hit 0 degrees if you have enough heat added. Okay. So it all depends on how many heat you have added. So Q total equals to, that's the total heat. All right. Then you can calculate what's this one. For this process, for ice to rise temperature to its melting point. Okay, so what heat is needed? You can call that Q1, right? And then if Q1 is less than the Q total, that means you have enough heat added. So then the ice will have phase transition, right? Temperature will not change, but it will have a phase transition. So you can calculate what's Q2 needed for the phase transition. And then you can compare Q1 plus Q2 to the total Q, okay? So in this case, if Q1 plus Q2 is still less than that, then you will have ice fully melted, okay? So in that case, ice will melt, fully melt. Otherwise, if Q1 plus Q2 is greater, then just partially melt, okay? Melted. So in that case, so you just have to check the numbers you got, okay? Similar here, if you have Q1 already greater than Q2, Q total, then it will just raise, temperature will just raise up to a certain point over here, not reaching 0, okay? But you could have like the Q total that is still greater than Q1 plus Q2, then the temperature of water at this point, right? Because then your ice will fully melt, it becomes water. So then it will rise up to a certain temperature. Okay, so you have to do step by step calculating like heat needed for each step and then compare to the total Q, or you add up the heat from previous steps and then compare to the total Q. Okay, and you might have it reach to 100 degrees, right? Then it will vaporize. Okay, and then so this will be Q3, this will be Q4, and then if you still have enough heat, then the vapor will have temperature increase. Okay, so you'll just have to compare step by step. Okay, and then see where it stops, and then you can calculate the final temperature. of the system. Okay. Here, Q2 should be just equal to the mass times latent heat of the fusion. Okay. So the fact that the problem didn't tell you latent heat for vaporization, so that probably gives you a hint that it will not reach at that temperature probably. Okay, so it's likely it's just going to stop somewhere here. Okay, so let me just give that hint out to you guys, and then you can try to see if you can figure out this final temperature here. What's this final temperature? All right. So there are several responses in already. We can take a look here. So Q1, we will have to calculate Q1, Q2, Q3. Okay, and then that's probably it. But and then we can add up each one as we have them into the previous Qs. So Q1 is the heat needed to increase the temperature of ice from -5 to 0 degrees. Okay, so it's going to be mass of the ice, C of the ice, times delta T in this case. I'm going to say delta T1. So the mass is 1.1 kilogram times for the ice is 2090 joules kilogram times degrees Celsius. Delta T will be 0 minus -5. Okay, so 0 is the final for this process, -5 is the initial. So this would be 11495 joules, or roughly 1.15 times 10 to the 4th joules. Okay, so this is less than the Q total of 5.2 times 10 to the 5th. Okay, so that means this temperature of ice will rise to 0, and then it will undergo phase transition. Now let's calculate how much heat is needed for the phase transition to complete. So that will be mass of the ice times latent heat of fusion. Okay, that would be 1.1 kilograms times 335 kilojoules. Okay, so remember it gives you as kilojoules here, so times 10 to the third joules kilogram. So that would be roughly 3.69 times 10 to the fifth joules. All right, so this is Q2. Now we have to see what's Q1 plus Q2. All right, so Q1 plus Q2 would be this guy plus that guy, 1.15 times 10 to the fourth plus 3.69 times 10 to the fifth joules. Okay, that gives us about 3.81 times 10 to the fifth joules. This is still less than Q total. Okay, so that means the ice will fully melt. Now it turns to water. Okay, then there's still heat remaining that is added to the system. So then this water will have temperature increase, right, to a certain point, T final. Okay, so I'm going to call that Q3 for that process. So Q3 should be equal to the mass. Again, should be the mass of the ice. Now it becomes water, so that mass stay the same. When there's phase transition, the mass doesn't change. Okay, but specific heat capacity, you want to change it to water because now it's water. It fully melted times delta T. Let me also call this delta T3. So this is 1.1 kilograms times 4186 joules kilogram degrees Celsius. Delta 3 should be T final minus 0, right? For this process, it starts from 0 degree to final of TF, okay? All right, so then this Q3, it should be the remaining heat, right? After these two parts. So then that Q3 should be also equal to Q total minus Q1 plus Q2, right? So that's equal to 5.2 times 10 to the fifth joules minus this guy's 3.81 times 10 to the fifth joules, okay? So that's equal to 1.39 times 10 to the fifth joules. Now it also equals to this expression. So you can set the two equal to each other and solve for your T final, okay? So then T final will be equal to 1.39 times 10 to the fifth joules divided by this 1.1 times 4186 right? That gives you about 30.2 degrees Celsius. Okay, you can just say 30 because it's given as 265. Okay, for the knowns. All right. So we assume that it's going to just be somewhere here, right? T final. So that's between 0 and 100 degree. So your final answer is 30, about 30. So that's well in that region between 0 and 100 degrees. So that means your assumption was right, okay? So if it turns out this to be more than 120 degrees, that means your original assumption of TF to be between 0 and 100 was not right. So then temperature of this will rise up to 100 and then we'll have phase transition. Okay, so then you have to judge again, calculate Q3, and then Q1 plus Q3 should be still less than Q total in that sense. Just assuming that this is a greater number than 5.2, say maybe 8 times 10 to the fifth or whatever, then you are probably in this either somewhere here or somewhere there above 100 degrees. Okay, so you have to calculate again then in that sense. All right, questions you guys might have? So if not, we are going to check on another example here. I think. So I think this happens um, very often, like in summer when you have to, when you want some like drink, you probably want to add some ice, right? So you can calculate what's the final temperature of your drink after you add the ice there. So this is one of the example. So it says a large punch bowl holds 3.99 kilogram of lemonade, which is essentially water at 20.5 degrees Celsius. A 0.0550 kilogram ice cube at minus 10.2 degrees Celsius is placed in the lemonade. What are the final temperature of the system and the amount of ice, if any, remaining? It says ignore any heat exchange with the bowl and the surrounding specific heat capacity for water is 4186. For ice is 2090, and latent heat of ice melt is 335 kilojoules again. So in this scenario, it's a little bit more complicated than what we had in the previous case, right? So now you have ice and water mixture. So what happens here? Let me just give you guys a head start on this. Again, you can draw like temperature as the vertical and then heat as the horizontal here. You are starting with ice and water. So let's say ice here, minus 10.2 degrees. And then water as, so lemonade is pretty much just water, okay? Basically, it's just water there. Water starting at 20.5 degrees Celsius, all right? So you can see now, you can have a good sense here about what's going to happen, right? Because you have a lot of water here. Water is 3.99 kilogram. Your ice is just a little bit, right? 0.055. So that means the temperature of water is going to drop a little bit, maybe, if not a lot. Okay. But for the ice, it's going to heat it up, increase temperature will increase, and then it will melt, most likely. And then for the melted ice becomes water, the temperature of that part of water will increase, reaching the same temperature of the ice. Okay, so then this would be your T final. And you're looking for that T final. All right, now you have two objects in contact ice and water. So you should apply conservation of energy. It's assuming there's no heat exchange with the surroundings, right? So then you'll have to calculate Q of water, all right? And then also Q of ice. Then the two should add up to be 0 because one will give out heat, one will receive heat. So that means for one of the Q is going to be negative, one of the Q is going to be positive. The other is going to be positive. So the two should add up to be 0, okay? And once you add the two up, these two Qs should be in expression with as a function of T final. And then when you add them up, you should have one unknown in the equation when you add the two equal to 0. Okay, so I'll give you guys a few minutes to try on this one, and then we can take a look on the solution together. So you can see the final temperature is going to be somewhere in between, right? In this case, it will be probably in between 0 and 20.5. If you get any number that is not in that range, then it's likely that doesn't look good. All right, let's take a look here. See quite a few responses in there already. So QC or QIs is going to be coming from three parts. So temperature of ice rise from minus 10.2 to 0 and then melt, and then for that melted ice to be temperature to be going up again. Okay, but for Q of water, it's going to be just one term. Okay, so Q of water should be mass of the water, C of water, delta T of water. Okay, and then for Q ice, it's going to be coming from those three parts. We can calculate them one by one. So for the first process, our first part is going from minus 10.2 to 0. Then that's mass of the ice, C of ice. Okay, so be careful about which C you want to plug in. This is still ice, so C of ice. Delta T1, that would be 0.0550 kilograms times 2090 joules over kilogram degrees Celsius. T1, delta T1 will be T1 final minus T1 initial, right? So T1 final is 0 degrees minus 10.2 degrees, okay? So that would be, I calculate this, 1172.49 joules for Q1. For Q2, it's going to be equal to the mass. This is phase transition now, the temperature doesn't change. Mass of the ice times latent heat of fusion, 0.055 kilograms times 300. It's given as 335. I was using 334 for some reason, but 335000. Okay, it's in kilojoules. So joules per kilogram. In that, so I probably don't have this number right, but I got 18370. Okay, should be a little bit larger than this, but just slightly. Okay, that's how much you would have about. Q3 is going to be from here to here, final temperature. So be M of ice. Okay, although it's water, but it should be having the mass of the ice initially. C now of water, you should use C of water, delta T3. Okay, so 0.055 kilogram times 4186 times TF, right? Minus 0, basically. This would be 230.23 times TF in joules. Okay. All right. And then, so this is Q1, Q2, Q3. All right. Q1, Q2 are just numbers. Q3 is expression with the TF. Now for QW, maybe I can write QW here. QW is equal to mass of water, C of water, delta of T water. Okay. So 3.99 times 4186 of T final minus 20.5 degrees Celsius. All right. These two, 1 minus 3.99 multiplied by 4186 will be 16702.14. Okay. So then this is 16702.14 times TF minus this number multiplied by 20.5. So minus 342393.87. Okay, that should be in joules. Okay, but that's your QW. All right. Now you have QW in terms of TF. You should have also Q1 plus Q2 plus Q3. That's Q ice. That's also in terms of T final. Okay, so you are going to add those terms up. So Q1 plus Q2 plus Q3. This is for Q of ice plus QW. That should equal to 0. Okay, let's see. All right. So then 1172.49 joules plus 18370 joules. You should have a number that's slightly larger than this, but about the same, okay? Plus 230.23 TF plus 16702.14 TF minus this number 87 to be equal to 0, right? So then in here, your TF is the only unknown. You are going to combine these two together, okay? So your T final is going to be equal to 342393.87, okay? Because you move this guy to the other side, and then this and this also to the other side, becomes negative 1172.49 minus 18370 divided by these two add up. 230 plus 16702.14. Okay. Sorry, it's out of the range there. All right. Okay, so move this guy to the other side equation, and then also these two. Negative become positive, positive become negative. Okay, so minus minus, and then combine these two together for the denominator. You'll get your T final. Okay. So T final 19.1 roughly. I think I round this up already. So it's probably like 90.0 something, 05 or 06. Okay, but about 19.1. So yeah, 19.1 is within the range between 0 and 20.5. Okay, so that sounds like reasonable. Okay, so if you got something greater than 20.5, then it doesn't look good. If it's less than 0, then this assumption is not valid. Okay. All right. Questions from you guys? So probably in one of your homework problems, or maybe two, but I don't remember. So you might have like a problem like this. Now the difference might be you have less water, but you have a lot more ice. Okay, so in that scenario, you might have the situation of so a lot of ice, small amount of water. So then water temperature may come down and then has phase transition and then freezes. But for ice, because you might have a lot of ice, it will just temperature will just raise up. Okay, so then you are having the final temperature somewhere here below 0. Okay, so that might be what you have. Okay, so just check on amount of the ice and water and then see what's likely going to happen. Okay, and then calculate the Qs, determine the final temperature from there. Or you might have maybe just the ideal amount of water and ice, so then the final temperature will be 0. Okay, so that's another scenario. Like it goes up here for ice and then freezes or melts partially, and at the same time for water it goes down and melt partially. Okay, so you might have a scenario like that too. So there's a lot of different possibilities you have to think about. Okay. All right. Any questions you guys might have? Okay. All right. So then the next section here in this chapter talks about mechanisms of heat transfer. So how heat is being transferred from one object to another object, or from one place to another. Um, so there are three different types of heat transfers. Um, so this figure here summarizes all three of them. Okay, so there's radiation. If you have a fireplace, fire gives out radiation to the room. So radiation can so in that case, heat can transfer without medium. So it can transfer in vacuum. So another example is the sun. When the sunlight reach us, so that's radiation heat, right? Because between Earth and the sun, there's vacuum. So radiation can go in vacuum, can propagate in vacuum. So that's radiation. Um, there's this heat conduction from the wood to the floor here. So that's direct in contact. So that's called heat conduction. And then there's convection. If there's airflow through here, so heat is being carried along with the airflow. So then heat goes from one place to another place. Okay, so three methods are all here. Also in here is convection because airflow goes up, so then heat being carried up. Okay. So let's take them one by one. If you have a conduction, that means you have direct in contact of the two objects, maybe through another physical body or maybe directly in contact. Okay. So there's one object here, one object on this other side. Okay. So then the power of the heat transfer, basically the heat divided by temperature difference, or derivative of heat over derivative of T. That's proportional to a K constant called thermal conductivity of the rod. So that's determined by the materials. Okay. So each material will have its own thermal conductivity of K. A is the cross-sectional area. Difference in temperature, TH minus TC should be, or maybe better modified by according to the figure T1 minus T2, okay, in that sense. But if T1 is greater than T2, okay, and divide by D, the distance, all right, or should be L. Sorry, the figure and the equation here doesn't match up, but L, okay, for the distance here between them, all right. So this table here gives you the thermal conductivity of the materials. So typically metal has a lot of high thermal conductivities, right? So your cooking appliance, some of them are likely to be made of metals like pans, etc. Although these days you have ceramics pans, but a lot of time we still use metals. Okay. All right. So typically, solids have higher thermal conductivity than liquids, and then air has the smallest. Okay, or gas. Gas has the smallest. The second method of heat transfer is called convection. That's the flow of fluid due to difference in temperature. So then the heat is carried with the fluid as well. Okay. So for example, again, in the if you have air circulation over here in the house, then heat can be transferred from the fireplace into the room, other places of room. Um, in summer, for example, in the at the shore here, close by the shore here, so land warms up quicker than the water, so then it's hot, warmer here, it's cooler here, so there will be air circulation going in that direction, carries the heat. Okay, in the nighttime it's the reverse because water cools off more or more slowly in that sense. Okay, the last one is called radiation. So fire, basically, if there's a fire, the radiation will come out. But in more general, any physical object that has temperature greater than absolute zero will actually give out heat. And then at the meantime, it will receive heat from the surrounding as well. Okay, so it's the two-way process. All right. And for the flames, the temperature can be determined or can be indicated by the color of the flames. Okay. All right. So the amount of radiation for any physical body, so it's equal to Q, the heat it gives out. Now, if you divide by time T, that means the power, okay, of this heat radiation is equal to a sigma, which is called Stefan Boltzmann constant, which is this number. E is the emissivity. It's between 0 and 1, depending on what material you have. Okay. And A is its surface area, the object surface area. T is the temperature in Kelvin to the force power. All right. So this is a radiation of heat for an object. And then, as I said, at the same time, the object will receive radiation from the surrounding. So if the surrounding has a temperature, say T1, the object has T2, or actually the other way around. Yeah, object has temperature T1, surrounding has temperature of T2. Then the heat transfer, the net heat transfer by radiation is given in this equation. All right. So in that case, if T2 is greater than T1, then the object receives heat overall, okay? Otherwise, it gives out heat. We'll take a look on this example here. All right, so it says calculate the net heat loss in radiation energy for a naked person in a room at 20 degrees Celsius, assuming the person to be a black body with the surface area of 1.4 meters square and the surface temperature of 33 degrees. So you probably realize that you have to convert the Celsius into Kelvin first, okay? Because the temperatures are not SI unit. I think I'm going to just show you the solutions here as we are running out of time. So in this case, you'll be using this equation of, so power is equal to energy divided by T, right? Q is energy, it's heat divided by T. And then this equation, sigma times E times A times T2 to the fourth minus T1 to the fourth. Okay. So sigma is the constant of 5.67 times 10 to the minus 8. And then 1.00 is the emissivity given of the skin to be a perfect radiator. The area, surface area, okay, and then if you convert T2, okay, to be, that's the surrounding, so that should be 293, okay, it's 0.15 Kelvin to the fourth minus, so this is converting from 20 degrees Celsius to Kelvin, okay, and then minus 306 Kelvin to the fourth. 0.15. This is 33 degrees Celsius to Kelvin. The result will be negative of 110 watts. Okay, so that means our body, if the surrounding is about 20 degree, our body gives out about 110 watts of heat. Okay, so you might heard of this, like our body is like 100 watts of light bulb. So that's coming from this approximation here. And the term here called black body, it doesn't refer to the skin of people. It just refer in this terminology is used in physics. It's called, for any object that gives out radiation, is called a black body. So pretty much like everything is a black body in that definition. Okay, because everything in the universe gives out heat. Okay, and then at the same time it receives heat as well. All right. So I think let's one quick video here about the method of how heat is being transferred. So let me just play that for you guys.